Hello, this is SND College of Engineering and Research Center, Yeola. Lecture series for first year engineering, Engineering Physics. I, Dr. Chaudhary Vivek Sitaram from first year engineering department. Now today's topic is about the free electron theory and position of Fermi level in intrinsic and extrinsic semiconductors. As we know from the how band theory evolved, band theory of solids, as in the wave functions and from the Heisenberg uncertainty principle, and we are giving the energy levels. So if we consider a single atom, then the electrons are revolving around the atoms in different levels. So these electrons are having different energy levels. It is in the splitted level. So just we can observe over here. So if this is electron, then it is having the energy E1, E2. The electrons are revolving in different orbit. So in E1 orbit, they are having energy E1. In E2 orbit, they are having energy E2. Similarly, if this is an other atom, non-interacting atom, so it is also the energy level is split up. But if these both atoms come closer, come together, they are interacting to each other, and the radius R is equal to its diameter. The distance is equal to radius. So both are contributing their electrons with each other. Then what happens? These energy levels are split up into two. So here E1 is split up into E1 into E2, E2 is split up into E2, E2 dash. So if we again come closer, interacting more than two atoms, so these energy levels are splitted in three levels. If again E2 will be splitted in three energy levels, and if we are brought together more than three atoms or four atoms, just like the energy levels are splitted into number of energy levels, number of atoms according to that. So E2 will be splitted according to that. So every atom is associated with its own energy level. When two atoms are placed apart, then they do not interact. Two atoms close together causes particular energy level to split into two energy levels. Now band theory of solid explains how energy bands are formed within the solids. Now if energy, when we are observing that energy level is split up, here energy level is split up, so according to their atoms, so here is the band, then according to that the outermost orbit, the electrons in the outermost orbit, so whatever may be the band formed from that will be the valence band, and after that whatever may be the electrons which are empty, whatever may be the shells which are empty, there is no electron or one or two according to that. So to consider at this stage there is no electron but shells are empty. So though there is a splitting of energy we are considering, and whatever may be the bond form, that is the conduction band. So energy band structure of the solid corresponding to the actual spacing of atoms in the body is given in the figure A, and energy level splitting as a function of distance is given in the B, and discrete energy levels in an isolated atoms. Now in energy band diagrams, so energy level splitting and energy band configuration of a silicon is given over here. So here again, if we observe that, so there is a filled energy levels and empty energy levels. So whatever may be the contribution due to empty energy levels is given as a conduction band. So whatever may be the field is contributed to the valence band. And the energy levels given splitted, that is just like the 1s stage and 2s stage. So these are given lower here. Their energy levels are, though it is splitted, but their contribution to the external field are very much less. So valence band, the band formed by series of energy levels containing valence electrons is called valence band. It may be completely filled or partially filled with electrons. Now conduction band, the band formed by energy values of free electrons that have broken their covalent bond is called conduction band. Conduction band is the next permitted energy band. It may be empty or partially filled with electrons. Now what is forbidden energy gap? The energy gap between the valence band and conduction band is called the forbidden energy gap or forbidden band or simply band gap. This band is formed by series of non-permitted energy levels. Remember this thing. This bond is formed by series of non-permitted energy levels above the top of valence band and below the conduction band. So in this region, not a single electron can stop over there, because there is no such an energy level where the electron can permitted to stop over there. There is no energy level. So energy gap is denoted by Eg. Now there is a valence band which may be partially or completely filled. Then there is energy gap. So valence band completely or partially filled, then energy gap, that is band gap energy, and the empty or partially filled according to their contribution of electrons in the particular atom. So there is a conduction band. Here the electrons are present whose covalent bond has been broken, and they can easily take part in the conduction when we are applying for the external fields. So material which do not conduct current is called an insulator. So in this conduction band and valence band separates with large energy gap which is greater than 5 electron hole. So according to classification of solids is on the basis of energy band diagram. So if the band gap energy is very large, it is greater than 5 electron hole or equal to 5 electron hole. So it is called as an insulator. Whereas in semiconductor, so the band gap energy is small and it is of the order of 1 electron volt. So the band gap energy Eg is of the order of 1 electron volt nearly. But in a conductor, the valence band and conductor band may be partially overlap or completely overlap. So material in which conduct the current is called conductors. As valence band overlaps with the conduction band, energy gap is 0. So current easily flow through these materials for the external this. Now types of semiconductors. As we know, there is a semiconductor. The name itself suggests that it is partially, sometimes it will work as a conductor, sometimes it works as an insulator. So that's why these are termed as a semiconductor. Now there are two types, intrinsic semiconductor and extrinsic semiconductor. Now what is intrinsic? Chemically pure semiconductor, that is 100% pure semiconductor, is generally termed as an intrinsic semiconductor. An extrinsic semiconductor doped with some external impurity are called extrinsic semiconductor. Now doping, it is a process of adding impurities into an intrinsic semiconductor, is generally called as doping. Now here consider the intrinsic semiconductor. In intrinsic semiconductor, there is 100% pure semiconductors, just like silicon, fourth group of an element, or 2/5 group, or 3/5 group, or 2/6 group. So from the periodic table. So band gap energy is 1.12 electron volt at 0 degree Kelvin. Remember these things. As the temperature we are going rise, then what happens? Some of the electrons take part in the conduction. So, and the band gap energy will change. So they will take part. Now N-type semiconductor. If we dope material from 5th group of periodic table, that is pentavalent impurity, P, AS, SB, are called N-type semiconductors. As pentavalent impurity atoms donate free electron, it is called donor impurity. Now if third group element are doped, just like boron, aluminum, gallium, indium, then they are called as the p-type semiconductor because they are trivalent. So there is one electron deficiency, so it will treat it as a whole. So as an acceptor impurity. So acceptor impurities create discrete energy level close to the valence band. So now here the concept of holes. Holes is nothing but the absence of electron. And deficiency of negative charge can be treated as a positive charge. Holes are positive charge carriers. Movement of electrons from nearby side gives rise to the movement of holes in the opposite direction. Holes is just like a bubble in a liquid. Now what is Fermi level and Fermi energy level? For conductor, the highest occupied energy level at 0 degree Kelvin is called the Fermi level, and the energy corresponding to it is called the Fermi energy level. I repeat, the highest occupied energy level at 0 degree Kelvin is called the Fermi level, and the energy corresponding to it is called the Fermi energy. For semiconductor, Fermi level is the reference energy level, and it corresponds to the center of the gravity of conduction electron and valence electron. For semiconductor, it is the center of gravity of conduction electron and valence hole. Now, what is Fermi Dirac distribution? The scientist Fermi Dirac has shown that. So, Fermi energy is equal to 1 upon 1 plus exponentially E minus EF upon kT, where E is the energy, EF is the Fermi energy level. So, for conductor, the highest occupied energy level at 0 degree Kelvin called the Fermi level, and for semiconductor, the reference level, Fermi level is the reference energy level, and it corresponds to the center of gravity of conduction of electrons. Now, effect of temperature on Fermi energy level. So, in this diagram, as we are seeing, probability of filling the level. So, here as the energy of the level, and here it is given, so probability of filling the level, and the temperature graph is here. At 0 degree Kelvin, it is exactly at the center, so there is no. So, E is equal to EF, so Fermi energy level. But as we are rising the temperature, so Fermi energy level probability will be increases. From 0, it is here is the 0, so here it is decreasing. What happens at 0.5%? It is the center of gravity. But as we are going for, as the temperature rises, the probability of finding the electron in the upper band rise, so it will goes towards the 1. Okay, got this? So now how this will happen? Fermi level in an intrinsic semiconductor. Now we just see. At 0 degree Kelvin, the number of electrons in the conduction band equals the number of holes in the valence band. So it will lies exactly at the center. But as the temperature rises, the effective mass of an electron and holes changes. So according to that, so Fermi energy level will changes. Now for p-type semiconductor. Now p-type material is, there is an acceptor impurity, where we had doped third trivalent impurity. So trivalent impurity means what happens? Number of holes concentration is larger than the number of electron concentration. So it is a density of state, electron states. So obviously from the center, this Fermi energy level shifted towards the low, because the holes density is more than the electron density. So to balance this, the Fermi energy will be lie at the center. Okay. Now, the number of holes in the valence band are greater than the number of electrons in the conduction band. So Fermi level shifts towards the valence band. With temperature, Fermi level shifts towards the upper level. Now similarly, Fermi level in N-type semiconductor. In N-type semiconductor, we had doped fifth group element, that is pentavalent impurity, phosphorus, arsenide, antimonide, PASSB. The number of electrons in conduction band are greater. The number of electrons in conduction band are greater than the number of holes in the valence band. So that's why, so the Fermi level shifts towards the conduction band. So here from the center, Fermi level shifts towards the conduction band. So now variation of Fermi level with impurity concentration in N-type semiconductor. So if we are having low impurity, so Fermi energy level shifts just like this. If here moderate impurity, Fermi level again shifts upper. If Fermi level energy at high impurity, then it will shift at large into the conduction band. So as per the carrier concentration, Fermi energy level shifts. So now we will shift towards the drift current. The current due to motion, that is drifting of charge carriers under the application of electric field is called drift current. Until and unless we are applying external field, there is no influence. Whenever we are applying external field to that substrate, to that material, there is a force of attraction due to potential difference, and the charge carriers are drifting, they are getting some velocity, and that is nothing but the drift current. And drift current density is given by number of electrons, then their mobility and energy. So for holes, there is a drifting according to that. So now diffusion current. So directional movement of charge carriers due to the concentration gradient is called the diffusion current. So whenever we know from the nature's law, there is a diffusion current. Now conductivity of semiconductor will be depending on the mobility of holes, mobility of electrons, number of electrons and number of holes. Okay. Now for n-type semiconductor, so number of donor impurity, electron and mobility of that electron. For p-type material, number of acceptor impurity, that charge and mobility of the holes. And for intrinsic, there is equal percentage of electrons and holes, so there is a sigma is equal to NIE mu E plus mu H. Okay. Now when we are shifting to our concentration towards the PN junction diode. The diode is just like a current valve. It allows unidirectional flow of current. Diode conduct only when it is forward bias and do not conduct ideally in reverse bias. It is used in rectifiers, and diode has a nonlinear VI characteristics, that is voltage current characteristics. Formation of PN junction diode. As we know, holes are the majority charge carriers and electrons are the minority charge carriers. In P region, electrons are the majority charge carriers and holes are the minority charge carriers in N region. When PN junction is boundary between P-type and N-type semiconductors, so the charges will be diffused. There is a diffusion of charges and formation of PN junction depletion region. Now, so their charges are depleted, that's why there is a depletion region. We will see in PN junction in detail. So here we are just viewing it. So when PN junction biasing is there, forward biasing and reverse biasing. When P terminal of the diode is connected to the positive and N terminal is connected to the negative terminal of the battery, so it is called the forward biasing, and reverse of this is in the reverse biasing. What is important for us? The distribution of Fermi energy level in forward bias and in reverse bias. So energy band diagram of PN junction diode at equilibrium mode. Due to charge density, the charges are diffused across the junction. So that's why the Fermi energy level is always constant. According to this, the bands are arranged over here. So this we are assuming. So Fermi energy is exactly at the center. Fermi energy is exactly at the center of the PN junction diode. So what is? Here is the P-type material, here is the N-type material. So Fermi energy level in N-type material, it is nearer to the conduction band, in P-type material it is nearer to the valence band. Now when we forward bias this, then what happens? The band gap energy, in forward bias, the charges are depleted and we are getting the sum of the electrons are already present in the nearby. So the holes will be shifted towards this conduction band, valence band of the N-type material, and electrons will be shifted towards the conduction band of the P-type material. So charges will be flow according to that. So electron drift and electron here holes are drift due to applied external potential. So according to that, we are getting the VI characteristics of the diode. In forward bias, so current due to majority of charge carriers. That's why here the current in forward bias is in milliampere, and in reverse bias the current in terms of microampere, because the current due to minority of charge carriers. Now we will see Hall effect in the next lecture. Thank you.